If we're doing piping calculations from one point to another, then we need to take into account the changes in elevation, local pressure, and velocity, and so on. So for example, if we were pumping water uphill from location 1 to a reservoir up on top of a mountain at location 2, we'd have to write Bernoulli's equation, Z1 plus P1 over rho g plus V1 squared over 2g equal to Z2 plus P2 over rho g plus V2 squared over 2g. That would be if we had no energy added or removed, no losses due to friction, no energy added by a pump. But we're taking what we've got at 1 and we're adding an increase in head across that pump. So we're putting energy in with the pump. So that adds on to what we had at location 1 here. If we go over to location 2, along the way to location 2, we've lost energy due to friction and minor losses. So we have what we had at 1, plus whatever we had in the pump, minus whatever we lost along the way. So what we'll be left with, plus the head loss due to friction, plus the head loss due to minor losses from location 1 to location 2, will give us a balance on our Bernoulli equation. So that's the head loss due to friction between 1 and 2. Those are the minor losses between location 1 and 2. And of course, head loss due to friction, F L over D, V squared over 2G. That's the Darcy-Weisbach equation, and this friction factor relates the flow and the geometry parameters of the piping system to the head that's lost as the flow goes through that piping system. We have a similar equation for minor losses. The sum of all the minor loss coefficients in the piping system, again, times V squared over 2G. Or if we combine them, delta HF plus delta HM equal to F L over D plus sigma K V squared over 2G to solve our problems. So if we're pumping uphill, we add the pump energy over here and take off the friction over there. If we're going downhill from location 2 to location 3, then we'll do the same thing. We'll write Bernoulli's equation, Z2 plus P2 over rho g plus V2 squared over 2g equal to Z3 plus P3 over rho g plus V3 squared over 2g plus anything that we lost along the way. So delta HF from 2 to 3, delta HM from location 2 to 3, and if we have a turbine over here, any energy that we took out as shaft work on that turbine, any energy that was the head drop across the turbine. So plus delta HT. So now we've accounted for putting energy in with a pump, losing energy due to friction along the way, losing energy due to friction and minor losses along the way, and possibly losing energy due to energy that we're taking out doing useful work on a turbine. Now, we've chosen these points 1, 2, and 3 to do our analysis on because they're easy points to terminate our Bernoulli's equation on. And I won't cross them out in this instance, but observation here, location 1, 2, and 3 are all at atmospheric pressure, so the pressure terms will go away. They're all at zero velocity, so the velocity terms will go away. And the only thing that turns out to be important is the elevation difference between 1 and 2, or 2 and 3. If we had a pressurized tank on top of the hill, then the pressure difference would matter. And it would just show up, we'd need to know what the pressure difference is, it would show up in addition to the elevation difference. Likewise, if we for some reason wanted to do our calculation before the water came out of the pipe here, then we'd have to pick another location here, and we'd have to account for the fact that V2 squared over 2g wasn't equal to 0. But we can make our lives easier by picking points where it's easy to specify the conditions. The velocities in all of these terms are the velocities in the pipe, and we're assuming that the pipe is all the same diameter. If the pipe had multiple different diameters at different locations in the flow, then you'd have to do multiple different calculations for the losses, taking into account the fact that the diameter was different and thus the velocity was different. That covers doing piping calculations from point to point. The other alternative is in a recirculating system where the water is pumped, or fluid is simply pumped round and around and around.